completion and currently guides 3 PhD scholars in addition to supervising several MTech students and BTech also. His research contributions are reflected in 40 research publications along with 8 book chapters and numerous international conference presentations. His achievements also include a Best Presentation Award at the International Conference in Toronto and recognition of his work as one of the best engineers in technology by the Department of Science and Technology, Government of India. We are delighted to have Dr. Bhimavaram was with us today and we warmly welcome him to his faculty development program. And confident the session will be highly informative and engaging for all the participants. Thank you.
So start thanking the this opportunity to keep in front of my research. Congratulate coordinator and other coordinator. Uh, and I'm very happy to meet Professor Parma sir. He's also I'm happy to know that he's also. So we have good discussion. So about this J2, J2 3. I would like to talk about this fuel cells. How it is related. You agree on that fuel cell also is a storage. How automatic area is see the third line of your hydrogen energy storage. So my whatever I'm talking about the fuel cells, that is also this energy storage. Because hydrogen in the device, the electrochemical device, generated. So when the renewables are there, when the trainer is the expert in electrolyzers, so the generated using the renewables, we have two amount of renewables we are generating. Technology is very much developed. There is renewable energies like solar energy, wind energy. And we are not amount of energy we are generating day by day. The technology is being improved. But bottleneck is here. We have to store that energy. So the battery technology is taken right now. Like that, stored that whatever energy is generated from the solar sent to the electrolyzer in the form of hydrogen, we are stored. Then we will supply it to the solar to generate it. Now, hope you understand how it is stored. Fuel cell is also storage. So, how we have seen the details. Before that, I would like to talk about our institute, Bhimavaram. Here from I am very proudly present, working in the Institute Engineering College, Bhimavaram, which is that is established in 1959, has been given the foundation stone. Recently, in this year, 2019, we have celebrated 60 years of completion. Now we are going forward. Top among the nations. So these are the research areas. I work in fuel cells, flow batteries. Mainly I make these membranes for the energy devices, fuel cells and flow batteries also. Also I started this work treatment. Which is diversion from the research. So application again, here also I synthesize materials for the you can say that advanced oxidation techniques of wastewater treatment, that is electrochemistry. So again, the membranes which we can in that I connected my dots, whatever expertise we have in electrochemistry, electrochemical engineering, to the wastewater treatment. So these are the few projects I have handled. I have collaboration with Newcastle University. that is in UK, and the Manchester Metropolitan University. These are the two universities I have collaborated with and I also visited UK to on the project. And I also completed the print project, which was in wastewater treatment. That is collaborated with the prime textiles near to the native Andhra. And this is the paid outcome of that print project, which is funded by DSC. One patent, and we could transfer the technology to that prime textiles. So this is my teaching and research profile. You can see my details. That is publicly available. Type my name, you can find that profile, teaching profile, which is posted on NIT Marangal website, Department of Engineering. And this is my Google Scholar profile. Over civilizations as 15 and I can index as 20. So coming to our details about my student myself, and this is the demand. You can see on the slide different sector by energy demand. This is the generation and this is the demand. Mostly we have higher demand on industrial sector. Whatever energy and electricity we are producing, that is most utilized in industry. There we have to focus. We are shifting the gears towards the renewables. And how we do that? This is the renewable energy. How we can use that renewable energy? This is the wind energy, solar energy, wave energy, geothermal energy, which is linked to this electrochemical energy. This electrochemical devices, which I am telling about, one is fuel cell and another is battery. I am focusing on that. This electrolyzer, CO2 electrolyzer, which gives me some useful products. We have to tap this energy, whatever available renewable energy. We have so much energy available out there, and we are able to tap it now. We have technology to tap the energy, but of tapping it, we have to store the energy whenever demand is there. We have to energy. So this is the energy outlook. They have predicted the fossil fuels by 2017. They predicted that the fossil fuels, whatever coal waste we are using now, that will take 58%. Then remaining renewable energy they will contribute to 31%. But now we are going forward. We want to make it 50-50. 50 from the fossil fuels, 50 from the renewables. Now we are very much inspiring everybody finding electrical step towards the renewables. So cost wise, what is the recent report? Solar energy now starting point. They are coming little cheaper than the other energies. Nearly $50 per megawatt. Now I will compare. This is about the fuel cell. This one is this statement is given by the reporter in marketing India. See, this is the published in Harvard Business Review. This statement about the fuel cell, that is at the time when we have said that the score of non-utility companies are well advanced towards developing a powerful technical fuel cell which could fit in some hidden process for every home silently taking out electrical power. That means no new connection is required when you have fuel cell at home, as you are putting that inverters in one cupboard. you are using it. Same way, if you put this fuel cell at one place, that will give you the power for your day-to-day maintenance. So, what is fuel cell? Why it is necessary for fuel cell? So, first thing is we have limited resources. Only in fossil fuels are limited. They are not there. Going to be. I don't. This statement we used for last 50 to 100 years. Everyone is saying that it will be depleted in the future, but still we are dependent on the mostly on the coal-based power plants, thermal power plants. So, but the thing is, those are limited resources. They are depleted or not, but when you are keep on using those same resources, they will be depleted in one day. But unlimited resource, that is renewable. So the shift we have to take. Second, this is the first point. Why we have to take the fuel cell. And fossil fuels, when we are using, they cause environmental problems. They generate CO2, greenhouse gases. So these are two interrelated problems. So now, what is fuel cell? It is simple electrochemical device. Energy converter, hydrogen energy, we are giving as an input, and it will be converted into the electricity. These gases. Again, we use the converters. In this part, we can use the. So you can see that now we can put it as a black box. But you know what is input, what is output. Input is we have two gases, one is hydrogen, another is oxygen. Output is electricity main thing, and as a byproduct, we get some heat. This is exothermic reaction. So heat will be liberated little bit, and the water will be formed. So this is fuel. How it is available, and that is explained here. Little history about fuels. I won't go into deeper details. He is a profession is alive, but he is a scientist, scientist, and this British scientist, they have to know this what are the causes problem. Science, 8 class, 9 class science problem. You connect it to the battery and connect to the electrodes into the water. You are producing this hydrogen and oxygen, two gases converted from the water. This is the electrolysis. And now this scientist got little reverse engineering. So when you are giving the electricity, you will produce hydrogen and oxygen. If you can combine this hydrogen, can you produce this electricity? That is the origin of the problem. How we got it. So the reaction itself is here combine these two gases and produce electricity. How you produce? Through a electrochemical device. We name it as a fuel cell. So we got the point that after that so much research has happened. He has built alkali based fuel cell and generators. And the size also matters, right? When we are looking for the application. And these are the fuel cell powered. Some devices, there is a car. In 1993 itself, first thing is Toyota. They have taken the lead to put the fuel cell into the car for transportation section. And if you see that fuel cell they started in 1990 and then been increasing trend. Now also you can see a lot of applications in you search for fuel cell applications and any other publishers. You will find a lot of applications fuel cell. So this is the fuel cell stack cell. The research in fuel cell that this is the 10 cell stack, and this is multiple cells. This is 45. These are taken from the fuel cell store. This is a 3 kilowatt and 40 volt cell. Okay. So this is the application. This is tractor is powered by the alkaline fuel cell. This is way back. Now you see that industry. Now if you go to the industry, you may not find this much clean because here there is no other gas. No, so this is very clean energy. So you are maintaining very much clean. They are producing the electricity. If you visit any thermal power plant, so these are the advantages. Why you have to focus on fuel cell? This is the direct energy conversion. First, one cell, you are giving that to gases and you are producing the electricity. There is no intermediates. Take that plant, many steps. Okay. So there is no moving parts. If there is any moving part in there, that efficiency will go down. Here there is no moving. It is silent. There is no noise. Load, and you can operate this fuel cell from the lower temperature to higher temperature, minus 20, minus 40, minus 20 degrees to you can go up to 80 degrees from fuel cell. Here even we have higher temperature fuel cells also, which operates like solid hydrogen fuel cell and it operates both of them. 1000 degrees. So sitting ability, we can give it anywhere. Fuel flexibility, hydrogen, oxygen. If you go to the higher temperatures, you can use air out, which internal reformer will be there. When we go for the higher temperature fuel cells, it itself steam we can reform. So you can have that methane reformer inside, and the hydrogen will be produced, and it will be supplied to the fuel cell, and will generate the electricity. So disadvantages, because it is as we have the advantages, we already exist, so we have some disadvantages also. These are extremely expensive, and we need this hydrogen infrastructure. Now India is more working on this, taking out this hydrogen infrastructure, and we need pure hydrogen for efficient conversion. It is so that purity of the hydrogen depends how far we are efficiently producing that quality electricity from the fuels. So these are the cell design part. Then how we design that fuel cell? Now fuel cell, we have the membrane one side, and other side is the figure. One side we have the membrane, that is a separator, and one side we have the porous electrode, other side which acts as an anode, and other side which we another porous electrode. Okay. And these three electrodes, two electrodes, that membrane is sandwiched between the two electrodes. That is called MEA, membrane electrode assembly. Okay. So the catalyst layer maybe is our definition whether we want to put that catalyst layer to the porous electrode or membrane. So this is called MEA. So the cost, it is now $73 per kilowatt. What happens? The power which we are getting from the comparable for the transport section, automatic internal combustion, that is about $25 to $35 per kilowatt. transport applications. Now we have to bring this 73 to 30. That is our target. Now it is cost more than enough. So we have to bring down this cost to this level. Then we can do this. So this is the breakdown of the cost. One is mainly about this platinum catalyst layer that takes little less than 47%. Then it is a membrane. These two costs are high. We can avoid the membrane with relative humidity. Membrane is operated at 90 to 100% relative humidity. Humidified membrane is required because of the transport of this H+ ion, proton exchange membrane. So for that, if we can make membrane which don't need this humidity condition, then we can reduce this membrane and thermometer thing. We maintain the loss of humidity and we need that humidity gas. We generate that humidity gas at a temperature and we have to send to the gas into the fuel cell. So we can avoid more problems. We can work on this membrane. This is one research problem. And if you can work on the catalyst. These two problems I have also focused on. And alternative catalyst, metal oxide based I have worked on. And the membrane also alternative membrane, which we can easily synthesize at laboratory level. That also I have worked on. So these two problems I have addressed in previous weeks. And durability, reliability, you can see that we need to operate this for stationary application these many hours. This is the temperature that minus 35 degrees to 45 degrees. Then only we can sell this product in the market. Okay, these requirements, market requirements. Then it is a durable, reliable, then only market accepts the product. So this is the product specification which our fuel cell should achieve. Again, the size also matters. When you put it that you are seeing the product which is powered by the alkali fuels. This improves the system, which is kept in. But if you can reduce the size with a little battery, you are putting in the electrical vehicles. Same way, the fuel cell size also, if you can make it with compact, we can put it on car. Then you can use this fuel cell in the transportation section very easily. So I already talked about this membrane electrode assembly, which has this is the membrane which allows selectively only H+ ions. This is the anode side porous electrode, and then this is the cathode side. This is the also one electrode. Then catalyst layer is a part of electrode. This is the thin line of the thing. This is the catalyst layer. This is the gas diffusion layer. So gas is entering here. It has to reach here for the reaction. Here hydrogen is entering and OT is entering. As you see that lab was taken. Two input we are getting. That is hydrogen and oxygen. Hydrogen is one side, anode side, and oxygen is other side, cathode side. So this both thing, it is not thicker than 200 microns and generates current density up to 11 watt per centimeter square. Electrode area. This is we have generalized because per centimeter square when we are taking, then we need not to mention the system size. So whatever centimeters that can be whatever system. If you are increasing the electrode area, then automatically power scale will also be increased. So these are the design features. After the assembly, after this, what we do here, we have that bipolar plates and current elements. again. This total MPA again will be sandwiched between the two bipolar plates and current collectors. Bipolar plates, that bipolar plate, it will be used as an interconnector for the in the stack. If you are getting or not getting, this is the chemical required gives the design. So this is the MEA understood, right? Membrane and two electrodes. That is these two assume as anode. This is the anode type bipolar. This we assume as a cathode type bipolar. This will have no channels. For hydrogen gas, and it will go if we have a certain node design here, gas will go from here, hydrogen, and to this side oxygen. These are the two bipolar plates. What it is direction of the gas flow, and it will that gas which is putting in there that will pass to the porous gas increase in there, electrode, and it will reach the catalyst surface where the reaction is. So this will give you the take over the current. We will put that and there as current collector, copper current collector, or any current collector. It's not something to demonstrate.
You can show them.
Okay. Oh. Dr. Sanger is from the industry. So yeah, this is the bipolar. You can see this is the FDP. Two. This is the gas equation there. This is gas equation there. This is the napkin membrane, which is sandwiched in between. This is the carbon club electrode. This is the lab scale small sector. Industrial scale we have bigger. So this is the gas which will be there electrode. On this we look at chemistry, platinum, chlorophyll, and what right. And this is the membrane. This is the membrane. So you can have this.
That is gas. This is membrane. Yeah, that is gas.
This is gas. You are not. This is gas.
This is membrane. Sir, I have
This is membrane in between. This is flow phase. Gas will enter here. Gas will enter here. This will. It is a direction for the gas. Surface gas, and it will leave from. This is one side is anode, other side is cathode bipolar. So intertime. So one side acts as a side, other side is a cathode. So here we will send oxygen. Here we will send hydrogen. So this is a in stack in single cell. It is a interplay. We will close it. When we have the multiple cells, then it will become interconnected.
Which power you mentioned 11 watts per centimeter square?
We can get whatever power we need, accordingly we design ourselves and design ourselves.
This single.
We can have the bipolar plate even bigger. 10 centimeters.
Typically, how much getting power?
It is based on the capacity. That's what Sir is explaining. Based on the MEA performance only you can get the power.
Even we have to increase this electrode area per centimeter square. You can calculate how many centimeters square according to the power you want. You can increase this centimeter square area.
This already.
No, sir, we can increase this is 10 centimeters square. You can have 100 centimeters square.
This gives.
Yes, single. You can, if you have a stack, then it will be multiple. That. So, and if you want to have a look, is output of the chain. I will look at that. Yes, battery option. This is a cell and the multiple cells in the stack.
What is the of that? Okay. One stance.
We have
One sentiment.
level what
Is there any dependency on hydrogen and the oxygen gas molecule?
based on we are getting out.
Yes.
So input gas purity is important and usage also utilization also more gas we have to send to the cell. When we send the sufficient gas pressure, it will react and will generate the gas. It is an ideal case when you are putting the distributor mileage, you have to operate at ideal cases. Same thing. So many situations are there.
Spirit of hydrogen is one of the important. Yes.
For the low temperature conditions.
Low temperature.
But higher temperature conditions, purity is not important. It will take care of itself. Again, we will get it. Then, so you have seen that objects. So this is the typical cell. This is one unit single cell. This is another single cell. This is the bipolar plate. This is the black color. So this side you have an again in between you have an NPA and you have the current connector. Generally you start. Then all stack is assembled in plates. So I have you. This is a single cell. You take in between you have a membrane, and this is the gas admission there. This is the catalyst there which we coating on this gas admission there. You have seen the black color. It is a carbon. We use as a carbon black also we use, and carbon plate also we use as a gas admission there. On that we put the kettles and this 1, 2, 3, 4, 5. This in between middle membrane and gas between there like this, gas between there like this. This whole thing we are taking as a MEA, membrane electrolysis. So this is the gas you have seen now. This gasket, other thing here, carbon cloth gas here, that gasket and bipolar. So this is the interconnector. Again, one gasket in the linkages, and we can connect another cell here, and we can connect another cell. This is stack. This single cell box.
Need to know what is the importance of the gas diffusion layer.
That is the electrode.
Next, catalyst membrane.
Catalyst is for decreasing that overproduction. Catalyst enhances that reaction.
So control.
For every reaction, you need some energy to initiate the reaction. So, if you have the reaction, utilizing the more energy, it is lost from us. So, we have to decrease the utilization of energy. So, activation energy, they say. So, we will decrease that activation energy and we can accelerate the reaction kinetics by catalyst.
Planting.
Planning. That is what
What about the gasket?
gas is about the leakages. Right. So this is the small video. Don't know if they are We have the possibilities. Small video. The currency of the design. You can see that how they are assembled this stack. That is the end plate. And this is the cell, single cell. So this is the one bipolar plate, another bipolar plate. This is the anode, cathode, which is membrane. This is single cell, this is stack. How it functions? This is a single cell. So here we have anode side, we are putting the cathode side, we are high oxygen inlet. So the reaction happens. It fuses through this gas diffusion layer, and H plus will be transferred through the membrane and reaches here and react with the oxygen, forms H2O and generate the electricity. It's the basic function of this fuel cell.
May I know the material of anode and cathode?
Anode, I have already told that graphite, carbon paper, carbon sheet, graphite plate. These are things are used for the as anodes.
Membranes,
Membrane napkin they are using commercial.
funnels.
Napkin, branded napkin. So currently we are searching for the reasons which are talking on that and synthesizing the alternate membranes for this napkin. One we have alternate membranes for this fuel cell, DMF, direct methanol fuel cell. That is given first PhD student. She has worked on this membrane. So,
Sorry, have you used it very often? So is it multi-layer blocking or
single layer, single layer,
single layer?
single layer carbon paper. It's a carbon paper. It's a porous carbon paper. So on that carbon paper, I have coated this catalyst layer. Catalyst ink we have to prepare. So the catalyst layer is coated onto the carbon paper.
Using
Very thin. Spin coater. Yes, drop coating. Yes, drop coating I did. It is further testing. Otherwise, I use the casting. Spin coating. Spin coating is the best thing which you can spread on the drop uniform. Different places you can put a drop and you can spin it. It will uniformly distribute. So this is the thing you have seen that video. In that you have seen that bipolar. These are the channels, gaps of channels. So this hydrogen, when we are putting through this channel, it will pass through this gas diffusion layer, porous gas diffusion layer, and it reaches this catalyst, that interface, membrane catalyst interface. There the reaction will happen. Hydrogen will split into, given the two protons and two electrons. So the electrons are connected to the electron. So the electrons are connected and the electrons are forced to pass through the external circuit, and internally the circuit hydrogen ion will be transported only this selective ion. Ion is selective to the, it is like act as a gate guarded you know allow any ion except H+. So it is proton selective ion membrane. So the H+ ion will be transported through the membrane and it will reach the cathode side. And oxygen, anyway we have supplied. Oxygen will react with H+ and you are found that electrons which are being forced that will complete the circuit here. The electrons will be taken from inside outside that will react and form the H2O. This is the blue picture, porous electrode structure, and this is the platinum, small platinum particles. This is the membrane. This is the interface where the reaction is. So, in this fuel cell, we have these 4 types of ions to be transported based on the system type of fuel cell which we have taken. In proton exchange membrane, H+ ion will be transported, and there are other fuel cell systems where oxygen is transported. Oxygen O2- is transported from the cathode side to the anode side to the membrane, and some fuel cell. I will see that I will show you the categorization of the fuel cell. Other fuel cell where it is minus is the transported ion to the membrane. Some other fuel cell CO3 is the transported ion through the membrane. So you are seeing that only H+ ion is transported, and we have in all the cases the overall reaction is H2 is reacting with both and forming H2 and delivering the electricity, generating the electricity. So when H+ is transported to the membrane, these are the oxygen reactions. When O2- is transported to the membrane, these are the oxygen reactions. This O2- is transported to the membrane and the reactive oxygen forms the H2O at anode side. Okay. And here H2 is formed cathode side. Then O2 this will react with and of the O2- will be delivered. That O2- will go to the anode side and form the H2O and 2 electrons. So overall reaction remains same, but based on the transport ion inside the fuel cell to the membrane that decide the oxygen reactions. This is when OH- is transported, then CO3 is transported. Where H+ ion will be transported, where OH- will be transported, where CO3 is transported. We'll see. This is the categorization of fuel cells. So, first one is alkaline fuel cell. The fuel cell application I told. You are seeing the tractor which is forward that is alkaline fuel cell. Then most famous and well-known fuel cell that is PEM fuel cell. They say that proton exchange membrane fuel cell. PEM fuel cell. And what is direct methanol fuel cell? This is the subset of PEM fuel cell. So methanol here is a carrier of the hydrogen. Okay. So then we have the phosphoric acid fuel cell and the molten carbonate fuel cell. Finally, we have the solid oxide fuel cell. So these 3 are low temperature fuel cell. These considered is 4 considered lower temperature fuel cell. These 2 are higher temperature fuel cells. Alkaline fuel cell, which ion which are transported? Alkaline. We have idea. It's OH- ion. So proton exchange membrane, it is there in the name itself, proton will be transported H+ ion. So direct fuel cell is a subset of proton exchange membrane fuel cell. So here also H+ ion will be transported. So phosphoric acid fuel cell. Phosphoric acid fuel cell. Again, it is a H+. H plus antiphosphoric acid. Molten carbonate solution CO3 2 minus. Solid carbonate solution O2 minus. So these ions here we are here. H2 is formed here. You see that here again H2 is formed cathode side. Oxygen is everywhere we are putting anode side H2, cathode side O2. And the formation of H2O only not where H plus is ion is transported to the membrane. There only we can see that H2O is formed cathode. Other side, other fuel cells like AFC, MCFC, SOFC, O2 is go from transported to H minus here. H2 is formed here and these are all fuel cells, right? Fuel cells. Operating temperature also, you can see that operating temperature. See up to here, we are operating up to 120 degrees. These are 600 to 650, 900 to 1000 degrees. MCFC and SOS, solid oxygen. So these have the internal reformers. So syngas is sent into the CO plus H2. That can be sent into the system as a fuel.
Is there any recovery of the waste heat?
Yes. Actually, heat thermal management is a different research area. People are working on water management and thermal management. So these two things are taken by the mechanical engineers mainly. They work on this recovery of heat, and we also integrate this heat to other devices. We are not focused on that release heat, but that will be played. And the heat, the temperature management, because we don't want if lower temperature cell, if it is reaching more than 120, then our cell will fail. So that heat has to be under control. The temperature has to be under control. So the thermal analysis, thermal management, this mechanical thermal people they are dealing with this problem. So they have this, some projects. So these are the basic reactions. Hydrogen is and electricity. So the heat is generated. So heat of reaction. They say that this is exothermic reaction. Any chemical reaction. So the reactions are developed. Chemistry, you know that, right? So here, this is an exothermic reaction. It is liberated. So here, you can see that this is delta H is minus 286 kilojoule per mole. So heat is liberated plus with the product. When we are writing separately, we will say that it's a reaction that matches 286 kilojoule per mole. So this is the heat of formation. How we calculate the heat of reaction? It is a specific heat associated with the formation of a particular product. This is little different chemistry. So you need not go with that detail, but you should understand that there is a heat is liberated because of that heat is energy associated with each of the compound. Okay. When the compound is formed from the elements, okay, the formation, the standard bit of formation will be there associated with that compound. Okay, when we are using that compound, so compound forms the products. Two compounds combined, we will have a product. Then heats of products and heats of reactants. That is your delta X, heats of reaction. So that here we have the reaction of H2 plus H2 because it is elemental. heats of formation is 0. H2, O2, it is elemental. There is no other element is associated with. There is no bar element is associated with in these two. Like H2O, here hydrogen is there, oxygen is there. But here elemental, we say that heat of formation is 0, standard heat of formation. So we have that delta H minus 286 kilojoule per mole. Please remember this. We are calculating the potential which we can generate from this fuel cell voltage. To say that V voltage we generate from this fuel cell. Here gives free energy. That means energy, useful energy associated with the system. That is, we call it thermodynamics delta G gives free energy. So enthalpy minus Ts. That is, Ts is entropy is the reversibility. So if you take out the reversibility, unavailable energy from the enthalpy, you will get a Gibbs energy, Gibbs free energy. So that is the useful energy associated with the delta G, H minus Ts. So you have the standard values. So these are calculated standard values. Data is available at this 25 degrees 1 atmosphere. This is the data, water as a liquid. This is the HF and SF, heats of formation, enthalpy of formation, entropy for the formation. So you can calculate the delta X and the delta H also. And from there you can calculate the delta G. When you can calculate the delta H from the standard values and the delta S from the standard values, you can calculate the delta G of the system. So here we have calculated that using those values. Delta G we got as 237 kilojoule per mole. So here heat produced is 48.68, but this value is important, delta G value, for calculating the voltage of the fuel cell. Okay. So here electrical work from the system, that is defined as Q into E, charge, that is coulombs per mole, into E, potential volts. That is the electrical work is defined as. So what is Q into E? Further, we can say that Q is this Avogadro number and charge of one electron is given. Then these two, an average QE, that gives you the Faraday's constant. That is Faraday's constant is standard number more than 96,555 coulombs per electron. So this is the Avogadro number. Now Q N F, here Q is equal to N into F, number of electrons into Faraday constant. And F E, it becomes theoretical energy. So W here is equal to N F E. Already we have seen that this is equal to the delta G, useful energy. So we are equating that LHS are equal, then we can equate the RHS. So vice versa, then two energies are equal. This is the energy of the fuel cell system. Electrical energy already we calculated. We are equating these two. Now delta G is equal to NFE. Now we need that potential voltage. Delta G by NF. Delta G already we have calculated. So delta G by N is equal to 2 electrons. We are transferring 2 electrons. So 2 electrons into Faraday's constant. Then what is 1.323 volts fuel cell voltage. Single cell will give you theoretical voltage, that is 1.23 volts at 25 degrees. So based on the how many volts you need, you have to put those cells in series stack. In single cell we are getting 1.2. So how you test this? You made this yourself, you are working on the materials, catalyst, or you work on the membrane, you assemble the cell. Then finally, how you are going to take this cell? This is the polarization curve. We will apply the load to the potential start. We will have the electrochemical start load there. where we can give that load, different load current, constant current, we can extract and we can observe the voltage. So as current is increasing, how the voltage is changed, that is the polarization. Okay. So the curve looks like this. There is a loss, voltage loss. We have to minimize this losses to have the high efficiency of the cell. If the losses are low, then we say that we lost much energy. We are not going to get that 1.3 we can get. So if these losses we have to minimize. These are the losses which are involved in the cell. One is because of the kinetics of electrochemical reaction. So each reaction to initiate we need some energy. So the energy is taken from this voltage only. Internal electrical magnetic resistance, that is ohmic loss, and reactants to the reactants sites, internal currents, cross reactants, because hydrogen may diffuse the other and directly. Because of this, you have many losses. This is the polarization curve where you have the current input and the response curve, response voltage you are seeing. It may have three regions. One is activation loss, second is ohmic region, ohmic loss, and concentration polarization loss. This happens at low current densities, low currents, that is activation loss. Once reaction is started, then the loss is mainly because of ohmic, resistance of electrode, resistance of membrane, and resistance of electrolyte. These are the losses you will face. Those are the constant losses throughout the reaction. When the current is increasing, then you will observe that concentrated polarization loss because of ions. Ions will come in their edges and they will form one layer at the surface of the. So those losses will be more at the higher temperature. So in this way we will test this fuel cell. So I will show you the DMFC, direct methanol fuel cell. That is also I will show you as a case study after this explanation. So this is the activation of ohmic loss, concentration polarization loss. So more losses are because of activation loss. Okay, when we analyze the losses, mainly these activation losses are more prominent than ohmic and concentration losses. So many researchers concentrated on this reducing this activation polarization loss rather than ohmic and concentration loss. This is standard losses. So how you can minimize this activation polarization loss? By using that catalyst. So if you can increase the kinetics of this reaction, if the reaction takes minimal current, minimal energy to initiate and go forward, then you can minimize this activation losses. These activation losses mainly with the kinetics of the reaction.
Will that 1.3 further come down?
Yes, sir. Because of these losses, it will come down. In reality, you will observe 1.1, sometimes 0.9. So if you minimize, then we can reach that voltage. It is theoretical cell voltage. So this is Butler-Volmer equation, which is closely related to this current and power potential. So here one analysis where we have the power potential, which we have to produce. Power potential is this is the standard voltage, 1.2 voltage we have. So is it E naught? That is the standard voltage. What? Because to initiate the reaction to all the resistances, we need to have, it will take more than 1.2. So that is the power potential, E minus E naught. The power potential which we need to reduce. Our aim is to reduce the power potential. We have to minimize the power potential. We have to, that reaction should take minimum minimal voltage to activate and go forward. Okay, so this is the current potential or potential. This reaction, anyway, this is the Butler-Wallace reaction, standard reaction by Butler-Wallace. This is the derivation and anode side and cathode side, same reaction have both, and anode side and cathode side, but sluggish reaction is cathode side, oxygen reaction. Hydrogen reaction will happen instantaneously. So we need not to worry about the hydrogen reaction much than this sluggish reaction and cathode side. Mainly potential levels are more cathode. So we are neglecting that other part. We are cathode side. This is the equation finally derivative. So finally we are taking this as a our war potential versus current. Okay. How it is analyzed? I will show you the data plot. First, here we can go on to tell the refracting. So, as I told, my battery got drained. Yes, kept the battery, but about the choice. It's not charging.
So, wait for 10 minutes. We'll get it. Okay.
kind of this slope, if you have the higher slope, that is slope. If you have higher slope, you have the higher voltage. If you have the low slope, then you will have lesser activation loss. Okay. So this is the derivation again. This is the electrochemical impedance spectroscopy. One technique which we can measure the resistance of the membrane or total conductivity of the membrane. Okay, total which we can measure by electrochemical impedance spectroscopy. You can search for this technique. You will get to know. So we worked on this BMFC as I told you initially. Direct methanol reduction. This is the methanol act as a hydrogen carrier. So CH3OH inside we have a hydrogen. That OH CH3OH overall it will give you CO2 6H plus and 6 electrons. And those H plus will react with the oxygen. And from here the overall reaction you can see that it will give you the 1.19 volts, nearly 1.2 volts. Okay. So what is the role of the membrane? Membrane has to allow H plus ions. It should not allow any other ion, and it should have the higher ionic conductivity for the H plus. Chemical resistance. We should have some chemical resistance and thermal stability when we are operating between some temperature range. It should have good thermal stability and it should not allow the other gases. Okay, when I synthesize the membrane for this BMFC, I have to see this is the contact angle. Why contact angle is important? In electrical also they have this contact angle. When the people who are working on the materials, contact angle is very important, whether the material is hydrophilic or hydrophobic. Contact angle is contact angle makes is that hydrophilic drop, water drop. When we put on the surface, it makes an angle on the surface. That is called contact angle. So, if it is hydrophilic surface, the contact angle is less than 90. It is less than 60 also. Even if it is less than 30, it is super hydrophobic or hydrophilic. Okay. Hydrophobic makes more air. If it is 110 or 110 or 125, it is all hydrophobic surface. But we need hydrophilic surface. Membrane has to be hydrated to transport the H plus side. So we need hydrophilic. So that's why we have taken the analysis of measuring the contact angle. Contact angle measured by the goniometer. You know that equipment. Goniometer. So this FTIR, Fourier transfer infrared spectroscopy. FTIR, you know that FTIR. This will give you the bonds present. OH bond, H plus bond, COOH bond. What are functional bonds present in the material? When we are combining the material, you need to analyze the what are the bonds present, the interaction happen between the particles of bond. For that, we need the Fourier transfer infrared spectroscopy. FTIR. You will have the spectrum. It will show you the spectrum. Then XRD, right? This analysis for the crystal. Crystal. What is the crystal phase and crystal size of the we can measure. This cell all well cell technique, you know, small quality. If you want to see the small quality, they use scanning electron microscope. With that microscope, we can take high resolution pictures and we see the surface how our coating is distributed on that material. We are doing the coating, right? The electrode surface and membrane also we are taking the base material and we are coating the other materials. So that thing we can see with this scanning electron microscope. And thermal stability we can measure easily. thermogravimetric analysis, and DTA, differential thermal analysis. So this is TGDTA equipment. Okay. Even we need mechanical strength of the membrane or redwood because we are keeping the material in the tight cell, airtight cell. That means we are tightening it. We are operating at a higher pressure, low to moderate pressure, not very high pressure. But for that condition, the material should sustain, should have enough mechanical strength. Okay, and proton conductivity, very important for the membrane. You are able to transport. Okay, so this is the way I have calculated the proton conductivity. Proton conductivity that is equal to L by A into R. This is the membrane resistance which I calculated by this technique EIS, and I know the area of the membrane, active area of the membrane, and the thickness of the membrane. So all these things I know, I can calculate the conductivity of the membrane. So in that way, I have this auto lab electrochemical workstation in my lab. So I connected this thing, the membrane in the cell. It is not this setup. I have another cell where I can put my membrane inside. Tighten the current volt thing, and I will put the KCL, normally KOH or KCL. So from electrolyte and I measure the membrane resistance. I measure the resistance of the cell, whole cell. Okay, with membrane, I will take out the membrane and again I will measure the resistance using this electrochemical application. Then difference between these two, with membrane, without membrane, that will give you the membrane resistance. So in that way, I have calculated this is the membrane which I synthesized in my lab, which has this 0.053 cm per centimeter, and our standard Napier membrane has the 0.066. I am working for the alternative to this Napier membrane. I want to propose our membrane. So this competitive, the Napier membrane is very costly, and making this membrane cost effective membrane with similar properties competitive. Okay. So, explain this technique. So this is the technique, electrochemical impedance technique. We are the response of the electrochemical system, cell, whatever fuel cell system, same system. Okay. To the applied potential. Potential means voltage we are applying, and we are seeing the response. The frequency dependence of the impedance can reveal the chemical process, what are the things happening inside the system. So I will show the plot and we will understand how the response. This is very much non-linear and complex. That's why we are taking the usually displayed in the netlist plot, using the netlist plot or border plot, we are getting this response. So this is the input signal, this is the output signal. We are giving the voltage, then we are potential, and we are getting the sinusoidal wave output and complex figure. That is the Z. This is the Z real. This is the Z imaginary. This is the Nyquist plot. Okay. This is the semi-circle wave plot, and from there we will have the other plots like this. This is the real plot. So this is the real plot. This is the imaginary plot. See, the up to here, when the imaginary part is 0, the real part is the ohmic resistance. That resistance I am taking it as a conductivity working R and resistance of the membrane. This ohmic resistance I am taking. I am zooming out this figure like this plot, and I am taking this value.
Is this read with the Warburg impedance? Warburg impedance.
This is completely
Different.
So this is the charge transfer resistance. After that, ohmic resistance, we have the charge transfer resistance. Here we have the conductivity. inductive resistance comes into capacity. So in this way, we analyze this thing, and here this ohmic resistance only we are taking, and we have calculated different temperatures of the membrane resistance. This is the proton conductivity to that, and we use that resistance to calculate the conductivity sigma value. So when we are increasing the temperature, our membrane proton conductivity is also increased. But after that, after 100, little reduction in proton conductivity we observe, because that membrane, it can withstand higher temperature, but the conductivity property is declining after some temperature. So that's why the optimum operational temperature we are putting on at 100, less than 100. Okay. So this is the
How do you control the temperature?
temperature control. We have a temperature controller. So we put the temperature controller. We have the thermal management system where temperature is measured from the thermocouples will be there inside the cell. That input will be taken, and it will be monitored continuously, and the cooling system will run, and it will maintain the temperature. So this is the polarization curve. This is the current density, cell voltage. This is the way we have the polarization curve at low current density and the higher current density. Each of the values cell voltage. This is the power density. When we are multiplying cell voltage with current density, we will have the power density. Okay. So voltage into current, that is watt per centimeter. So these values are power density, these values are current density at different temperatures. Okay. So the optimal power density, power density matter, where we could able to produce more power. That is important. In this way, we are testing the fuel cell. So that is where we are polarization curve help us the performance of the fuel, estimating the performance of the fuel cell. So power density we will calculate. Cyclic voltammetry, we are done with the electrochemical impedance, AICTE, where we can measure that impedance of the resistance of the membrane. So this is the cyclic voltammetry. What is the importance of cyclic voltammetry technique? This is the electrochemical technique again. So here input is voltage, output is current. Okay, so this is the input signal we are taking from the one and initial point to final point, and we can take that final point to initial point. So then how the response? So when we are increasing the voltage, the current is generated for initiating the reaction. So when the reaction is initiated, then electrons will be consumed or released. If it is released, then it is an oxidation. If it is consumed, it is a reduction. Okay. So in this way, at what voltage the oxidation happens, at what voltage reduction is happening, we will know the clear picture where the reaction is happening, how much voltage we have to give to the system. That is the cyclic voltammeter. This is the setup, 3 electrode system. One is reference electrode, one is working electrode, other is counter electrode. 3 electrodes, which we connected to the potential star. This is the way we generate the cyclic voltammeter. Okay. This is the input signal. Initial voltage to final voltage to initial. We'll sweep back. So from initial voltage, this is the potential window, and this is the current window. Here, when we started giving the initial input, this is the way the reaction progresses. We are getting the highest potential here, peak current, anode peak current, we will say IPA. Okay, this is the peak current at cathode, IPC. Okay, this is the peak separation distance. Okay, these are the main parameters which we see in the cyclic water. Okay, so at what potential it is oxidized? This is the oxidation peak. This is the reduction peak. Right? This is the anodic peak. This is the cathodic peak, reduction peak. This is the negative current. This is the oxidation positive current. Where we are getting, why we are getting the current? As electrons release are consumed. Based on this only, we get to know current is generated. Electrons are generated. So this is the cyclic model. This is the parameters which we have to see for. This is the analysis. So this is about the fuel cell. Little research oriented testing. Fuel cell, how we are tested. What are the techniques we used to test the fuel cell? So mainly we used electrochemical impedance spectroscopy, cyclic voltammetry, and to generate the power. These are the three techniques which we use. And when we are making the membrane, the case study which I have given, the membrane characterization, you are seeing from the contact and physical characterization, electrochemical characterization. These are the things. I will give you the paper where it's all published. So you can go to my Google Scholar profile where on this we have paper in Journal of Hydrogen Energy. Journal of Hydrogen Energy, it is an excellent journal. In fact, back from nearly 8 or 9. Q1 lecture. Two papers I have published on this one, and both are in Journal. Okay, so I'll talk a little about flow vectors. This is the second one. So necessity of flow vectors and all. I'll quickly cover because we have time constraint already. We are at 11:45. Okay, another how much time we have on our list? Wherever you are not understanding, able to follow, please stop me so that I can explain. I can spend a little more time on that. Okay. So, same way, we need to reduce the cost of storage. Okay. Fuel cell also we have the high cost. Here storage also has the high cost. So, if you can reduce the storage cost, we can afford the renewable energy. When we have the renewable energy, we are easily able to generate the renewable energy from the solar, wind, and hydro everywhere. But when we are facing the more cost in storage, so the generated energy we cannot use directly. As we are generating energy from the thermal power plant, it is sent to the grid directly. We are using it, but here renewable energy is intermittent. It is not generated all the time. Solar energy we can generate only daytime when the source is available. So then we have to store that energy whatever generated. When the demand is there, when we want to use, then only we can use it again. So whenever it is generated, we have to store it. Whenever it is not generated, also we have to do it. Okay, it is not like continuous generation or continuously usage. So we here bottleneck is thermal energy storage battery mainly. That plays major role in usage of the renewable energy. So for stationary storage, flow batteries are best, but stationary storage, their best thing is flow batteries for because it has the deep cycles, deep discharge cycles, and it is very stable. There is no explosion and anything. You can easily replace that. You can clean it and you can keep it back and reuse the electrolyte also. This way, flow batteries have the advantage. Those are details. So lastly, energy storage for the bottleneck, the rapid development deployment of critically important in order to create a clean and sustainable future. Yes.
So what does stationary storage mean?
Stationary, it is the key. You have mobile storage, lithium ion battery. You are able to put into the vehicle or you can use the for the transportation. It is easily you can take from one place to other place. Stationary storage means it is installed same place. It is very heavy. It has the bigger tanks, electrolyte tanks, which are connected to the cell, so you cannot move it easily from there. It is stationary energy storage. We say.
So, if it's the case, what are the main difference between fuel cell, hydrogen cell, and flow battery?
See, flow battery is the energy storage. Fuel cell is the energy generation device. It is a storage. It is the electrical storage. Battery. Fuel cell is a generating device. You are putting the fuel, it will generate electricity directly.
So, in the case, could you please fuel cell and hydrogen cell?
Both are cell. Hydrogen cell is same like fuel cell because hydrogen cell is like inputting we are putting the hydrogen as fuel. Then hydrogen is fuel cell. Hydrogen is the main fuel cell. So hydrogen fuel we are putting at anode side, and cathode side we are giving the oxygen. Because of the electrochemical reaction, we are generating the electricity. Same fuel cell, hydrogen cell, same. Both are same. Hydrogen cell and fuel cell are same.
Hydrogen cell is affordable for electric vehicles.
It is little expensive, but still people are, because of this water splitting, you can generate because of electrolysis process. If you use the renewable energy for water splitting, it is not an easy thing. It needs huge amount of energy for splitting off this water into hydrogen and oxygen. It needs more electricity than most water we are generating. Because gas is moving this. And we are using the renewable for splitting the water. Okay, we can go for it. So, if we can use that renewable energy, that is electrolysis. Fuel cell is reverse of the okay. Electrolysis we are doing starting electrolysis is we are giving the electricity and generating the hydrogen. Then we are land in the lower cell class A plus we are doing. Here fuel cell is combining the hydrogen we are generating the
Means to get the hydrogen and oxygen in order to burn the fuel cell, you have to undergo electrolysis first. To divide the water into hydrogen.
again we are need the energy to divide the water into hydrogen.
See, electricity is required in order to divide water into hydrogen. And again, we are generating electricity.
Yes.
Then I don't think there will be
Yes.
output.
No.
I mean, the efficiency may not, the overall efficiency may be less.
Yes. It is a common question when we are talking about this fuel cell or battery. It's a common question because people say that we are using that huge amount of electricity for producing the hydrogen, and we are using that produced electricity to generate the electricity. Both it is cost. If you see the life cycle, if you see the balance, where how much we use to generate the hydrogen, how much we have produced using the fuel cell, then that is not comparable. But here the thing is, that's why I am telling, if we are using the electricity which is generated from the renewables, solar, directly we can use the solar energy to split this water to generate the hydrogen. Then it is advisable to use the hydrogen generated to put into the fuel system.
To split it, we again need a renewable.
Yes, renewable. This is again we are dependent on the capture the renewable.
So if you can use the renewable energy, which is abundantly available, to split this water, generate the then now hydrogen is we got it free. We say, but we got it less price because we for that energy capturing also we need the device, right? Solar PV panels. So that cost also we include, and finally we balance it to the output, how much we generated. This is like hydrogen storing the renewable energy. By doing that, you are capturing the renewable energy.
Will it be affordable in the future?
Yes, then researchers are extensively working on this.
Because recently India has generated hydrogen.
Hydrogen infrastructure, to improve the hydrogen infrastructure, many projects are extended to this question.
So could you please explain, see, recently Indian Railways has introduced methods of locomotive.
Yes.
So could you please explain something about what were the challenges that basically behave and what the future will be? See, we replace the conventional.
Yes, definitely.
What are challenges and what the future will be?
And one more, sir, for his connection. So locomotive, but they are working, somehow they are successful for the movement of locomotive. But what about domestic, especially for many people are interested to save money. So in this point of view, the hydrogen
We are seeing the articles. Vehicles are running with water, only water is flowing. The vehicle is running.
After with water, but the water has to be let
Again, he is using the battery setup and he taking the electricity and splitting it in the hydrogen. The hydrogen is going inside, and then the vehicle is running.
can the system be economical?
Yes, to make it economical, only researchers working to make that whatever balance of plant or materials are costly. To reduce the material cost, catalyst we are going for alternative catalyst, not to go for platinum metal. And membrane also is very costly napkin. Instead of napkin, we want to go for less expensive. Performance wise, we are not compromising on the without compromising on the performance. We want to go for the alternative. So if we reduce the catalyst cost, then cell cost is extensively reduced. Then we can make that
We understand that membranes is just
membrane without foaming.
no. This
This is like a just separate. Have you seen that chili kitchen?
Yes,
Water filter. That is membrane separating. It is a separating cloth on here or normal cloth we are taking. These also we can say it as a membrane because it is a separating unit.
what is separating?
It is separating. If you put that when we are fetching water from the well, you are pouring through the top. Why you are pouring through the top? Separating out some particles, impurities from the water. Therefore, it is separated. The principle is here size exclusion. Because of pore diameter is less than
Here, demineralization process is required, sir, it is not required. Demineralization.
Demineralization. Completely if you demineralize it, you mean from difference of the body, right? Completely,
If you go to thermal power plant or anywhere else, that definitely is required. But here the DM plant is required in the hydrogen mechanism.
hydrogen is less. Water quality is also, it is also made the base. If you have more impurities, then it takes more energy to split. You need water also, it is purity is there. It is not same energy for the sea water. It is not same for the. It is different for the. Okay, energy difference. The product, the produced hydrogen quality also different. So it depends on the source.
Depend means actually here to produce the hydrogen gas, maximum will catch this river water only. Right, sir? In most of the areas to produce hydrogen, directly we won't go to sea, but we catch it.
It needs pre-treatment. It needs pre-treatment.
Yeah, yeah. Retreatment is required.
It has to go through that step, pre-treatment step. Then that pure water only used for that. Otherwise, it number the membrane, report, everything. So, this anyway you have seen. This is the capturing of this energy, solar energy, through the PV panels, and which we have want to store. We want to use and use this. So in between, we need this battery system. If you take out battery system, we cannot use directly the AC power. It is generated DC power. You can put the converter, but whatever it is coming, directly you cannot use it. So continue. But sometimes you may need it. After, see, now you are using for the laptop and energy. But I will close it again. But generation is continuously coming. I am not using it. That means I need to store it. I need a battery. Again, from that, I can use later. That time, the source is not there. Solar energy is not there. Right time. I want to use the generated energy. For that energy generated, I need to store somewhere. It is like a bank. You can say you are depositing and keeping the money whenever you need. You are trying taking out and